record. Smart shop. No, pre-recorded things I'm not returning back. So no. Please leave your autograms about your first and second choice. Last time we were collecting from the back row, now we're going from the first row, so that it will be even. So, no?
No.
Am I wrong?
You're fine. You can both put it on. I was like, there may be competition for point groups, that's all.
I don't want to do that.
Oh. So when do we do it? Do you want to do it next Thursday, or you want to a little? Right now you do have all materials to present even right now. Huh? No, Tuesday. I hate Tuesdays.
Why?
Because there is no lab on Monday. Like, some of us are very organized and some are a little less, and we should give equal chance to everyone. And some people prepare everything in the last like
45 minutes before midnight.
yeah, and then Wednesday it's a little better. So Tuesday is a reminder, Wednesday is preparation, Thursday is actual presentation. So we can do it either next Thursday, and probably thinking about next Thursday, but if there will be democratic voice of everyone, we can postpone it by 1 week so that everyone prepares it to the perfect stage. No one has travel plans for Thursdays? Everyone will be here? Good. I might be away coming Wednesday, so it will be either online lab or pre-recorded like instruction, but basically you have all skills that are needed for presentation. It is not voluntary. I just need to work at a different place for invitation. But coming Thursday we'll be here. So who we are and what are we doing? Let's recall. So we are trying to get practical skills to characterize materials through computational software. We split it electronic and nuclear degrees of freedom, and we are working on electronic degrees of freedom right now. We have agreed that it is too hard to deal with all degrees of freedom at once, and we set up general directions that we need to fragment multi-electronic wave function onto products of some sort, and then develop set of equations for individual one electronic wave functions, which we know are called molecular orbitals. When we met last time, we did non-practical exercise of forming multi-electron wave function as a product of one electron orbitals, and we have seen general directions of how it can be done. So it is possible, but we agreed that it is not quite precise. We need to take into account antisymmetry of the multi-electron wave function, and we need to take into account the findings of Dr. Slater. Okay. And maybe the last thing that was spoken out in the class on Tuesday, that if we are in a context of conversion from multi-electronic wave function to one electron molecular orbitals, we replace the word Hamiltonian into word Fock orbital, Fock operator. So our task, our goal is to set up Fock operator in a correct way so that it will be used later. So we believe to have equations for molecular orbitals, or in more technical way, equations for expansion coefficients of molecular orbitals in the basis of atomic orbitals. And these equations should take into account interaction between electrons, and it should be some form of electron-electron interaction term. But we want to do it in a more or less correct way. So right now we are filling the forms, putting your names to the subject that you would feel comfortable to present, because the practical skills that we are learning in the lab should be distributed evenly between everyone. So each of us will get a little more specialized in one subject, other one, and then we'll bring it up and share, and hope that technology will cooperate better next time, and we will be able to record and share recordings too. Okay, this is a little repetition of what we had on the black on the screen last time. So we are setting prescription how the Hartree-Fock method is working. So we start with positions of ions. We select the basis set, which is representation of atomic orbitals, and then we need to find expansion coefficients of molecular orbitals in basis of atomic orbitals, and then they come into multi-electron wave function and allow to find total energy. So we spent some time talking about Slater determinant, spin, justification of spin. I need to provide maybe answer key to the homework. There was one question when not everyone was perfect. The expectation value of S plus S minus operator, S plus plus S minus. Many of you put the answer equals to either expansion coefficient C alpha or C beta, or some of them, but it should be a product. So if you have bra and cat, and each bra and the bra has first power of expansion coefficient, cat has first power of expansion coefficient. If you merge them together, it should be second power, like C alpha, C beta, or C alpha squared, something like this. Until, right? I'll develop or copy the answer key and distribute, just for your curiosity. So this time we are going to develop the flowchart for Hartree-Fock, same as we did for geometry optimization. And now the word for today's meeting are correlation and exchange. It is two different parts, two different contributions that originate from electron-electron interaction. So everything we are doing today can be presented in 3 minutes. We are just going slow and sure to give an opportunity for discussion, to object something, to ask questions, so that we do not have intellectual shock. So this molecular orbitals as expansion coefficients is what we discussed last time. We need equation for those. It looks like I'm doing a little overview. And this is oversimplified cartoon of several electrons, finding spots in space were not filled by another electrons. And we are going to deal with electron interaction term. So in case we deal with only 2 electrons as an example, the wave function is constructed as Slater determinant, first function, second function, first position in space, second position in space, and here it is opposite. So we want to merge these 2 things in a careful and rigorous way, nothing else. So there will be a little surprise. Okay, so it is a visibility area. When I was in South Dakota, I was telling what does abbreviation SD means. Slater determinant. 1, phi 2, R2, and now we swap. We keep here phi 1, phi 2, but put here R2, R1. And we didn't prove it absolutely rigorously, but we did show that solutions of such case appear when we consider 2 spins. Single state get such combination of one of the functions. And it is a typical form for multi-electron wave functions. If one gets more than 2, it formulated in form of determinants. One writes all wave functions as elements and as in a row, and all positions in the column, and then find algebraically determinant. And it will be summation of all products with different plus or minus signs. But it will be too much for one meeting. Now, let's look on the total energy of the system, which can be thought of either completely abstract model of 2 electrons, or if you want to be practical, it could be H plus, not H plus, H2 mole. 2 binds to H. And we are looking onto total energy minus all kinetic energy and minus all energy of interacting between electrons and ions, just to define rigorously what we are looking at. So we are looking only on contributions that are coming from electron-electron interaction. So instead of big wave function that depends on R1, R2, we are going to bra of Slater determinant and ket of Slater determinant. And we are not going to do anything intellectual in the next 3 minutes, just opening the brackets, putting this expression here into there, and then seeing what we are coming at algebraically. So I have just started to write this expression. This is bra of Slater determinant. And these two integrals are coming from convolution. When we know for sure that there will be bra and cat, it means that we integrate over all degrees of freedom. And we put stars everywhere. Make sense? By now? Okay. Now we are writing here 1 over 1, 2, equals. And now we are placing the cat of this letter. This was bra, and here we are placing cat. One, 5, 2. These arguments in the same order. R1, R2. Minus phi 1, phi 2, with the inverse order, R2, R1. And it is not our fantasy, it is what we did show. Okay, what is the next step? Two open brackets and get 4 terms, because 2 times 2 will be 4. And each one molecular orbital here does have 3 symbols, 3 identifiers. So it has position, which can be either R1 or R2. It has number of orbital, which can be 1 or 2, and it is conjugation, which can be there is conjugation or there are no conjugation. First and first. This one is simple, we don't need to think. 1, 2, 1, 2, 2 divided by 1 minus.
Looking at a star.
Yes, I did. Now I did. With your help. Plus. And now let's skip second and third because they will be more ugly and need a little more thinking. Let's write the last one right away. So minus times minus will be again plus, and it will be R2, I2 star R1, 1, R2, I2, R1. So what can we tell about these two terms? So the orbitals of the same index are evaluated at space point of the same position. Right? And actually, if one integrates over R1 and R2, it doesn't matter in which order are they listed. It is the only symmetry is important. That indices arrangement of indices repeats here and there. And if you want to write it in a more pleasant way, or better, take this one, we can combine it as I1 R1 absolute value squared, and this one times, and this one phi 2 R2 absolute value squared. Right? Now we are coming to interpretation of quantum theory. What is the absolute value square of wave function? Huh? Probability in common interpretation. But there is a second one, less common, that wave function square is the density of matter. That probably we shouldn't put on the record, but it is how much of electrons are found in the vicinity of this spot. And if we understand that we deal only with occupied orbitals, each of which contain one electron, then this density, it's not just density of something, density of electron and density of charge. So these can be interpreted as density of charge corresponding to first orbital in position 1, density of charge in space 2, equal R1 minus R2, equal 1 and R2. So it does look same way as in classical mechanics. Charge 1 times charge 2 divided by distance between charge 1 and charge 2. So it is potential energy of Coulomb repulsion of two charges. So it is a simple term that can be interpreted classically. There are no intellectual challenges. Coulomb. I don't know, some people like different letters. It's not me. It is from the textbook. Any questions or objections about the Coulomb term that contributes to the total energy of multi-electron system? Looks simple. Coulomb repulsion of two electrons contributes positive value to the total energy. Positive contribution to total energy. So now let's deal with rest of the terms. One star R1, I2 star R2. From here, minus sign times phi1 R2 phi2 R1. So it is the second term, and you feel inside yourself that something is wrong, something is not typical. And now the term number 3 will also be with negative sign. So we start from here. Phi1 star R2, phi2 star R1. times phi 1 R1 phi 2 R2 divided by R1 minus R2. So can we simplify these two terms into the same interpretable form, where one combines those just to probability or electron density? Can one identify pairs where the wave function of the same index evaluated at the same spot? Let's look. 1, 1, 1, 2, no. 2, 2, 2, 1, no. So it is some crazy combination. But we didn't set it up. It is not a mistake. It is an immediate consequence of the antisymmetry principle. So we set up antisymmetry principle, we take Coulomb electron interaction, and we look onto all contributions. How do we treat it? How do we call it? So it looks like the orbitals are swapped, are exchanged in this expression. So let's not make it complicated and call it exchange term to the energy. So it corresponds to swapping of electrons. And I do not have this simple form, so it is one cannot simplify it further. It just looks this way. What is interesting and important that sign is minus. So this is a little surprise that we started with only electrons. All electrons have negative charge. They are supposed to repel each other and contribute positive energy. But here, due to antisymmetry principle, there are terms with negative energy, which typically corresponds to attraction. So due to this antisymmetry, there is a, how do you say in chemical language, stabilizing term that lowers the energy. So exchange term. Exchange term. Stabilizing. System of multi-electron system. So, and here is the difference between Hartree products and true Slater determinant approach. If you do Hartree products, energy will be consistently higher than on experiment, even in qualitative estimates. If one carefully takes into account antisymmetry, there is this term with minus sign that stabilizes the system and gets energy much closer to the experimental values, and overall trends and conclusions are much more reliable. I'm going to forget about one integration. write it explicitly. For get one of integrations. So if you have two integrations, if you have full convolution and brand cap, it will be a number. Total energy is a number. If you forget about one integration, it will be operator. So let's keep integration about electron number 2 and artificially remove integration about of the position of electron 1. And now I'm dealing only with Coulomb term. So if we remove the bra of the first electron, keep only cat of the first electron, and everything that deals with the second electron is left inside, then it becomes an operator of Coulomb interaction of whatever stands in front with the background charge, with the average charge distribution created by all but one electron, or in this case, by the second electron. So this red object contains influence of all but one electrons onto electron here. So it is an operator.
Shouldn't the phi 1 be squared?
If you want a matrix element, if you want a number, this will be an operator that will act on the wave function.
But
No. If you want energy, then we want to multiply it by conjugate and integrate. Right now we do not have conjugate and we do not, well, we do have integration, but we do not have conjugate. Let me check this so that I do not lie. And I found the way to edit recordings. If it will be wrong, I will just cut it off. So my memory was serving sufficient for 40 minutes. Now let's go to the cheat sheet. So we need Coulomb and Exchange. Here is what we did. So Slater determinant, electron interaction, two terms. I still need to jump between them. Okay, so the first type of terms were the index of orbital and position in space are the same. And second type of terms were the index of orbital and position in space are different. And these types of terms have negative signs. So stabilizing term in the total energy. So most important that it does reduce the total energy. So exchange term reduces the total energy. And let's see here. Whew. Good. So, if you take this part of the total energy, we can call it Coulomb operator of interacting with background charge. And then the question of Levi was that if you multiply by 1 star, J by 1, then we will get expectation value of this Coulomb energy. But without this multiplication, it is just an operator that acts on the wave function molecular orbital of the first electron. And we need to develop an analog of Schrödinger equation for one electron molecular orbital. So it will be a guy contributing to the Fock equation. Can we do similar thing for the exchange? Can we identify a one electron operator that at some time later we will plug into the equation for molecular orbital? No, we cannot without tricks. So here is the term, and with the same form. So we want to leave out
So why we write phi 1 R1 there?
let's take the term and make a correspondence with it. This term, two,
Okay, and then one is missing again.
and then
Then phi 2 R1.
yes, good, thank you. But we do want to make an operator that acts on the orbital number 1, not on the orbital number 2. So right now is a correct expression. But in order to maintain the same form, we'll write here phi 2 R1, and here we will write phi 1 R2.
And before that, phi 1 conjugate R2.
Hmm?
Have another term.
No, we deal only with one term. So in order to maintain the form in the total energy, it should be the blue gradient. But in order to have an equation for electron number 1, we need to have red gradient. Phi2R1, Phi1R2. And the understanding is that when we apply this operator to this function, before
So they have another part before that.
before the integration is completed, one needs to swap an wave function from the argument and with one electron wave function that is inside of this kernel. So it is a technical way that it is an operator that is not a self-contained. It is informed like an operator, but it takes what it acts on, replaces it in something inside, and then continues acting. So it is exchanging of the electrons. Okay. Equals integral dr2 phi 2 r2 phi 2 r1 times phi 1 r2. So if one designs, these expressions are equal, if one designs an operator that includes instantaneous swap of the wave functions, then it will be a term that one needs to complete Hartree-Fock equations. So one needs exchange term that includes this swap of operators. How one can survive it? How one can intuitively address it? It's not intuitive, it is counterintuitive. But there are people who deal with such stuff professionally, and they trying to find way to visualize such processes. It's not me. I'm not doing it for profession, but I will try to show you some pictures that professionals in this area are doing to make it possible to live with it. So first, Coulomb. one starts with phi 1 and one ends with phi 1 star. And then this 1 over R1 minus R2 is an interaction with second electron.
5 minutes. 5 minutes. Is it 5 minutes?
Yes, yes. So you have one electron, second electron, and a little spring between them, which makes them to interact and change their momentum, or whatever. Move in other direction, repel each other. How can we make diagram of this sort for the exchange term? So we start with phi 1, and then we end with phi 2. So we can do phi 2 was phi and phi, then deviated, and then they pass through each other. So they exchanged. Phi 1 became phi 2. And the Coulomb term is, this spring is somewhere on the side. And the common, not very bad. In some community, common notation is J and K. That I always miss what is J, what is K, and it seems like this one will be J, and this one will be K. Coulomb and exchange. So the swap of order of orbitals is represented by this lines that cross each other, and it does contribute negative term to the total energy. If one is programming this equation, there are ways to numerically represent an operator that takes into account swapping the orbitals. And when we meet next time, we are going to accept this counterintuitive Coulomb exchange term, and we are going to set up an equation for molecular orbital and a way to refine the expansion coefficients of molecular orbitals. Because if one solves it just once, it will be not sufficient. Then different electrons will have no chance to fill each other. They need to adjust each other through several self-consistent cycles. So when we meet next time, it will look approximately this way. The stuff that replaces Hamiltonian operator for one electron molecular orbital will include this small h for the member of Hamiltonian, which will include kinetic energy and potential energy of attraction to ions, and electron-electron interaction that is decomposed on two terms, Coulomb and exchange. Everyone is seen except.
I get out.
Okay, so I think we are about to complete the meeting. There are two things in the Hartree-Fock theory before we can make a record that we are done with it. There is a way to include a self-consistent cycle, and there is a way to convert all equations into language of expansion coefficients of molecular orbitals. Right now, we are writing everything as functions depending on position in space. So it is more, if we bring back kinetic and potential energy, it will look like standard Schrödinger equation with differential operators. And for numerical convenience, we may want to convert it into matrix equations for expansion coefficients. So two things left, matrix form and self-consistency. And then we will take Hartree-Fock as completed. Meeting is dismissed. Thank you for coming, and see you on Tuesday. I owe you the homework so that your weekend will be not boring. And I'm. Huh?
Thanks.
So there will be an opportunity. Yeah, pretty much. And there will be an opportunity to compute bandgap energy of all of your models and put it into one graph and make the density of states for each model and two orbitals for each model, HOMO and LUMO. I just need to overcome myself and put it in writing and distribute. Maybe through email, since we are departing and adjourning right now. So I will stay here to answer questions, but we are going off record.